Now we're going to have the workshop report backs, and then after this session there's going to be refreshments and posters. So I'm going to call the workshop organizers, and then each of them will give a summary of the discussion and presentation that have been at the workshop. So the first one is going to be the workshop on socially responsible human cyber-physical systems. And Noak is giving she should have some few slides, I think. There it is. No, it's okay, it's okay. Okay. I think you have this too. Wait.
Thank you.
Oh, I don't know if this works, but now you need to see. So this is for.
Okay.
Oh wait, there is no slide. Yeah. Start when I'm going to start.
Any chance you could show the slide again? All right, thank you. So my name is Noak. I'm representing Miko, who did most of the work here, but unfortunately couldn't be here today, and also Ufuk, who is co-organizing this workshop. So the workshop is on socially responsible human cyber-physical systems. Oh, okay. So specifically, what we target as the outcomes of the workshop is to answer the following three questions. Wait. Yeah. So the first question is, how do we define socially responsible human CPS? This is sort of open-ended question. And the other two more specific questions are, what are the advances, technological, societal, that are necessary to achieve socially responsible human CPS? And the last question would be, what are the opportunities or resources that are needed to achieve the advances in number two? So our panel include 4 experts in this area, Anu, Lou, Todd, and Dorsa, and I'd like to thank the panelists for sharing. Very nice, and we had a very interesting discussion, which I'll present the result right now. So the first question that we try to answer is, how do we define socially responsible CPS, human CPS? All right, so the first idea that Anu pointed out is that these systems have to account for social justice and equity, right? When we design and model and analyze the system. The particular application that she brought up is in smart grids, right? And in this case, we need to address the impact of the technology on the low and moderate income. And we also want to include reward function across participating and also non-participating agents. All right. So the second idea here came from Lou. This is where we want to adhere to the principle of responsible design, which is from the recent ACM document, which explicitly state accountability, and this is also in accordance with what Todd pointed out about responsible representations of algorithm. This is where we want to better explain what the system can and cannot do, which include also uncertain performance. The last bullet here, this is pointed out by Dorsa, is that the system has to adhere to design objective, transparent, and have to have graceful failure. All right, and here we should also include social responsibility as part of the performance objective. So how do we achieve, what are the advances that are needed so that we could achieve social responsible human CPS? Oh, sorry. So first of all, we need to be able to incorporate justice among different groups, like low income, as in the smart grids, when we frame the problem. We need to be able to specify human-like behavior it might not be clear, actually. Even, let's say we have traffic rules that we want to adhere to, but, not every people adhere to these rules, right? So the question is, how do we formally write this down, or even learn this specification and the reward functions from the data? The new methods that we develop should also automatically communicate its limitations and uncertainty. We also need a method to detect problems in our algorithms from the data. We need metrics and data sets for validation as well. We also need a method to solicit and act on the input from human operators. And we also need to incorporate input from all the stakeholders. Right? And finally, we need a mathematical model to capture the dynamics of human trust, which could change dynamically. Like, for example, how much human trust autonomous system, autonomous vehicle could change even just in one ride. So the last question here is, what opportunities or resources are needed to achieve these advances? First of all, we need measures, data set, benchmarks to help us create accurate models. Right? We need also standards for sharing the information. We need characterization of data sets with respect to desirable, socially responsible properties. We need standards of collecting data, right? We don't have a lot of data, and we better need more diverse and cleaner data. We also need workshops, projects, platform to bring the vast range of stakeholders, including those who have no access to traditional means together. And lastly, we need collaborations among different disciplines, engineering, researcher, policy makers. And with that, we'll need to develop a common language between these different groups. All right, this one, David, if you're not happy, this is not my idea. So the last thing that we ask our panelists is that if David came as a Santa Claus and could fund one of the 5-year project, what problem to solve. So these are the answer from our panelists. So energy justice, you could probably guess from whom this answer is from. Automated data curation, large CPS model, and means for CPS to communicate itself. All right, so that's summarize our workshop. Thank you.
Thank you very much. The next report will be from Asimina Gyurti, and she will talk about artificial intelligence for healthcare.
Hi, everyone. So I don't have slides. I'm going to go through my notes on what we covered. So our workshop was on AI for healthcare, and it had 2 portions. One was talks. We had 2 speakers. One of them was Rance Cleveland from the University of Maryland, and our second speaker was Rose Faggy from New York University. So I'm going to start with debriefs on these 2 talks, and then the second portion of our workshop was a panel. So both Rance and Rose were on the panel, and they're joined by Payam Haidari from UC Irvine, Jia Liu from Harvard University, and John Stankovic from the University of Virginia. So before starting here the debrief, I just want to thank my co-organizer, Fateme Afga, for helping put together the structure of the workshop, helping today with the event, and so on. So first I'm going to start with the talk we had from Rance Cleveland. So the topic he addressed was the differentiation between data mining, and data mining we all know, it's the idea of extracting trends and patterns from data, versus data mining, and by mine I mean mine, not yours, in the sense of a certain ownership of data. How does one data mining compare versus that data mining? Of course, in the concept of healthcare. So the issue that he highlighted was the fact that there are a lot of ethical and legal issues in case we have a medical system that ends up giving a wrong diagnosis. And the point to note here is that healthcare is actually very heavily regulated, may that be through the government or through the private sector. So then he highlighted opportunities for machine learning in healthcare, and he talked about 4 fields: diagnostic, therapeutic, research, and health management. Challenges, though, associated with those are data-related and legal or ethical, meaning if something happens, who is to blame? The prognosis turned out to be a bit pessimistic. So then the question is, what do we do to overcome that? And the idea that he brought up, and in fact that idea came up several times later on in the panel as well, was the idea of synthetic data, meaning that instead of having humans and collecting data on humans, can we develop some type of a simulation model that gives us a lot of data, and then we do our training and our evaluation on that synthetic data instead of the human data itself. So that concludes the first talk. Then I'm gonna move on with an update and a summary on our second talk that was from Rose Faggi. So she talked about the research that she has been carrying on for years on MindWatch, the idea being a wearable, a smartwatch, that can actually monitor mental well-being. So kind of a traditional concept, if you want to monitor neural or cognitive states, would be to monitor the brain itself, meaning you would have an EEG, electroencephalogram sensor being placed on the head. Obviously that works, but you cannot take an EEG device and walk out and do real-world activities. So her group's idea is to have instead a wearable, a smartwatch, that can indirectly infer these neural states and cognitive states. So what her group does, and this was the focus of the presentation, is to have physiological signals like skin conductance or blood cortisol infer neural stimuli. Based on those data, observe the cognitive state, and then have a closed-loop system where there's a control strategy eventually to maintain a certain neural state. So that's the idea of MindWatch. We saw some nice experimental results showing feasibility. And then we talked about some applications like enhancing productivity in the workplace, maximize cognitive engagement, aging in place, and pain management. So the second half of our workshop, like I said, was our panel. So we addressed 5 topics overall. So first one was about successful applications or successful cases of AI in healthcare today. All of our panelists, I think, agreed that number 1 successful scenario today is image analysis, mainly in cancer detection applications. They also highlighted healthcare applications. Several of them are already approved by the FDA. Mental health applications, cardiology, non-invasive brain-computer interfaces, and multimodal data analysis. The second topic that was discussed was the idea of generating large amounts of data. How do we do that? What challenges are associated with that? So that's when the concept of synthetic data came back into the table. And as I mentioned earlier, the idea of synthetic data is that instead of collecting human data, you have this simulation model that can help you generate, in this case, like big data. However, then kind of we switched the discussion and we said, do we really need big data? Big data, yeah, it's a hot topic, but it could be an overkill for certain applications. So we started discussing about what applications can actually use small data and what we can use with small data. And the idea of maybe just requiring signal processing and not machine learning. Of course, that's not really straightforward. We need ways to handle bias. We need, again, kind of ideas of developing those synthetic models to help expand upon this small data and so on. Third topic was the question of what is health data? And the thinking was that a few years back, the definition of health data was kind of straightforward. It's the data that your clinician collects for you. But now we're in the era of all these wearables and cameras monitoring. So what is really health data? And especially in the concept of security and privacy and accountability, how do we protect this data and what kind of data are we supposed to protect? So there's consensus that this is a complex problem and there's not a specific answer here because health is tied to well-being And if we talk about our well-being, then everything is health data. Even monitoring, like one of our panelists said, even monitoring if you went to a bar one night and had alcohol, that's actually related to your health. So then where does it end? And it's really a complex problem. The fourth topic discussed on the panel was the idea of ground truth. How can we find the ground truth in a clinical setting? The example that was brought up was an MRI image that maybe 4 or 5 clinicians look at it and they give you 4 to 5 different diagnoses. Again, you can imagine this is a complex problem, so there's no definite answer. But the idea was that today, if you talk to a doctor, if they don't know, if they're not sure, they might consult with another doctor, or they might refer you to another doctor. So we have consults and referrals. Can we add AI to the equation? The idea being having sensors that monitor the same data through different perspectives, use AI to derive a diagnosis, but eventually fuse that diagnosis with that of clinicians. And by clinicians, we mean like a great number of clinicians who discuss together to finalize the answer. Obviously, it was brought up that there's no such thing as ground truth, but I guess the idea here is to have the correct diagnosis. And the last topic that was brought up, it was really the last question where we said that throughout the discussion, there were a lot of topics brought up, from machine learning to big data, to signal processing, to sensors, and so on. So these are all completely different disciplines. Are we in favor of interdisciplinary training? Are we in favor of big teams? Obviously, the answer is kind of yes to both, but where is the fine line? And what was recommended was that we need our students to have deep knowledge on a certain field because that's how we can advance science. But it's good to be able to understand each other's language. So at the end of the day, we are going to have interdisciplinary teams. We should be able to talk not just with engineers or scientists in different fields, but also with clinicians. And we should have the training to be able to understand each other's language and communicate. So that concludes our workshop. If any of this inspired any further ideas, please let us know. Thank you.
Thank you very much. The next workshop that is going to report is Intelligent Autonomous Cyber Physical System Design, Verification, and Certification. And the reporters should be Peng Wei and Pierluigi Nuzzo. Here they come. You have some slides too, right?
You can visualize the slides. Can we project the slide? All right, thank you. Good afternoon. So the third workshop was focused on intelligent autonomous cyber physical systems, covering aspects in design, verification, and certification. So the questions, right, that motivated the talks during the session were the following. So what could be mostly centered on around assurance of intelligent autonomous cyber-physical systems. What could be a viable path toward accelerating the development and deployment of autonomy and AI mission-critical systems while still keeping their exemplary safety and dependability records of these systems? And when reflecting about the certification process and the amount of human bias in the process, the second question was asking, what are the science and technology principles enabling acceleration of certification even of AI-enabled mission-critical systems? We had the pool of talks from both university and industry, and covering several aspects of formal methods, verification, control, and certification. So from Francesco Borrelli with Safe Learning in Autonomous Systems, and then Samuel Coogan and Sriram Sankaranarayanan gave us their perspective on fast reachability as a building block for verified autonomy and predictive runtime assurance for autonomous systems. One talk from Hadzem Torfa, postdoc at UC Berkeley in Sanjit Sesha's group, talked about learning monitorable operational design domains for assured autonomy, and we concluded with Tim Wang, principal research engineering for Autonomous Intelligent System and Raytheon Technology Research Center on his perspective on design and assurance of autonomy in industry. So we'll now summarize the main takes of the talks and then the takeaway messages.
All right, thank you very much. This one is not working or work? Okay, all right. So the summary or highlights of the talks from not working. All right. How about now? Not working? Why is it otherwise? All right, so here we go. The first talk from Francesco. So he was talking about the safe CPS with predictive control, with safety guarantees and uncertainty bound. Complex CPS with the reason to introduce learning-based approach or data-driven approach is complex CPS with limited computing and questionable abstraction. So that's why he introduced the learning approach and data-driven approach. Now his group is moving to the safe cooperative robots, or basically safety on multiple agents. And then we have Sam talking about the fast reachability for verified autonomy using over-approximation. More specifically, his group has been working on the monotone systems, from monotone systems to mixed monotonicity for interval reachability estimates, because this approach will provide more faster and more efficient reachability analysis. And then from Shriyam, he was talking about the prediction with runtime verification under uncertainty, specifically how to use intention information or how to infer the intent or intention, and using the Bayesian type approach to make longer look ahead with better improved accuracy. The fourth speaker, Hazen, he was talking about how to capture the operational design domains, basically the environment that the autonomy is operating in. So the environment where the autonomy was designed for or designed to function, and focus on the, so he used the term called monitorable ODD, or operational design domains. So the framework involved with learning-based approach and using simulation-based testing, and find the counterexample, use the counterexample to refine the system. And then we have our industry expert, Tim Wang from Raytheon Technology. So he was talking about the automated assurance using decomposition and also the hierarchical contract nets, which is a Bayesian net sort of approach to capture knowledge, as well as the formal methods approach. His framework, or his team's framework, can also handle the stochasticity part as well. So those are the highlights of the talks. So next we'll go through some of the, the sort of like conclusions, or our group or our workshop believe those should be the challenges or future directions, or at least some of the challenges and future directions. The first one is safety in multi-agent cases, especially multi-agent learning-based agents. Also, neural networks in the loop control systems, George mentioned this morning. Also, the compositional guarantee, that might be a solid approach or a viable approach to move forward. And then Sam was mentioning how do we study the trade-off between offline verification and online monitoring. And also, Shriyam's point is use or infer intention to do better prediction, longer prediction and more accurate prediction in runtime verification. So Hazen brought up the, a lot of systems now. I mean, they are not black box. Some of the neural networks, those parameters are known, but oftentimes a lot of systems are black box to us. So those systems pose challenges to, clear specifications or clear requirements. So in those cases, we have to learn from, statistics, experiment design or statistics theory, so we can use them, use those tools to to do the simulation-based testing and identify the counterexamples, falsification, and go back to do the refinement. Finally, we talk about how to guarantee the completeness. So if I think we're done. We're done. Okay. All right. So so if we rely on the statistic-based approach for simulation-based testing, or simulation-based plus flight tests or road tests or real-time tests, so how do we guarantee or say something about completeness? Because a lot of us talk about the correctness, right? But when we talk about a completeness, how do we guarantee that? Or how do we, to what level of tests, or how many millions or billions of tests in simulation, or how many hundreds of tests on the road, we can establish the trust for verification. So how to capture the unknown unknowns, that's Tim mentioned. And also for those trusts, not only rely on the numbers, the sort of the statistic results or the test results, but also rely on the societal acceptance, especially the human trust, with those machine learning and AI models. So some sort of explainability was mentioning as well. So finally, we were, the group was talking about the technologies that allow agile system development or system refinement. So that way we can push out the product faster. So I guess that's what we have. Thank you very much.
Okay, the last workshop, I was the organizer, and it was about the future of cyber-physical systems. We had 5 speakers: Panagiotis Garava from Purdue University, George Papas from University of Pennsylvania, Miroslav Pajic from Duke University, Sumik Sarkar from Iowa State, and Saman Zonot from Georgia Tech. And let's see if this works. So these are the topics that the speakers addressed, and they cover what are the important research challenges in the future of CPS, what are exciting opportunities for CPS research in the next 5 years, what are the lessons learned, including what worked and what did not work, and what are ideas for technology transition to industry and society. So I tried to write down and organize the different points into these different categories. I'm not sure I did a good job, and I'm not sure what I did was complete, but I'll try to give you an overview. So definitely one point that was made is that many CPS, and especially human-centered CPS, are often heterogeneous. They require customized and costly solution, and this is definitely a challenge. Then when we deploy machine learning system in cyber-physical system, and again, especially in human-centered cyber-physical systems, then we often trying to learn different things, so have multiple learning objectives. Also, we have multiple sources of information, and this data, thank you. Okay, and this data is often affected by noise, and is only partially observable, and this probably came out in both the keynote talks that we had today. Also, in certain systems, and I think the most practical example is autonomous driving, having real-time detection of problems may not be enough, because if you say, oh, now we're going to hit a pedestrian, and then of course you're going to hit it because the physics of the system does not allow you to stop the system as it is running. So we need some sort of prediction that goes above real-time, so able to predict the future. Also, another challenge is while today we are able, at least in certain contexts, to provide individualized inference and monitoring, we are still not able to provide individualized actuation. And here the example was in the context of agronomy and smart agriculture, in which we are able to monitor and do inference on a single individual plants, but we are still not able to do some sort of decision-making and actuation in order to act on that plant. And also there are new technologies such as AI, edge computing, 5G, and autonomy that can converge together, and then they pose new questions that I'm not sure if these are challenges or opportunities, but anyway, I put it in this category. So where do we do the computation? How do we design the communication? How is the communication going to affect the machine learning and the decision-making in general? And also, how do we do sensing in this new context? In terms of opportunities, so in the context of intrusion response, it was pointed out that when it comes to response and recovery, this problem is not really much addressed in the cyber domain, and it's definitely not really addressed in the cyber-physical domain. Then there is also the need of domain-specific artificial intelligence for security. And one problem that actually came up also in the keynotes this morning, and how do we represent knowledge, and how do we incorporate machine learning models, how do we incorporate knowledge into these machine learning models? And an example of this is physics-aware models that take into account the physics of the systems, but in general, this could include also other types of knowledge that you know your system needs to satisfy. Along the same lines, also, how can we do optimal decision-making when we have limited information and limited data? And there is also a need from predictive and proactive situation awareness. And finally, it was pointed out that power consumption is still a significant limitation when we want to deploy this machine learning and decision-making solution at the edge or on small devices. And so neuromorphic computing is an opportunity in the future in order to reduce this power consumption. Also, one of our speakers pointed out some under or unexplored domains, and these include cyber-physical systems for environment sustainability, cyber-physical system for societal science, and to deal for societal science problems, such as, for example, dealing with misinformation. Also, how can we include human experts into cyber-physical systems, and how can we address sustainable computing in terms of data and also in terms of energy, as I mentioned before. And finally, how we can use cyber-physical system and machine learning that incorporate specifically ethics in their design. In terms of lesson learned, the speakers pointed out that we need to address and consider current practices because often us as scientists are a little bit disconnected from what is currently happening and occurring in the field. So we need to understand what people are doing today, the people that actually work in those problems, before we can design solutions that are actually going to improve their whatever issues and whatever work they're trying to do. So trying to understand what is done today in order to at least hope that what we develop is going to be adopted by the stakeholders in their domain. Then there is also lack of sufficiently large testbed to validate approaches. I think this was also mentioned in the previous report from another workshop. So we need a significant amount of real testbed and also significant variability of real testbed. This was pointed out, for example, in the context of smart buildings. So I think most of us don't even have access to one smart building, but even if we have access to one smart building, is that really general enough to say that whatever solution we are developing is going to work on a large scale? So probably not. So we need the ability to deploy and test our solution on a large scale. Then also another challenge is that as we try to test our solution, for example, using different simulators or using different data sets, these often come with different APIs, different formats that make very difficult and time-consuming to test our solution on many of them. So there should be more uniformity and make this process easier in order to test the solution on different data sets and different simulators, at least. Also, it was pointed out that some of this testing is relatively easier in some domains. So, for example, in the agricultural domain, do some examples, some experiments in the field is less critical than do it, for example, in a health CPS domain, in which you need to test on real patients, which of course is much more difficult and also requires much more safety in order to be even just authorized. Okay, and finally, we discussed also about how to make sure that there is transition to, not make sure, but at least help whatever we propose to transition into industry and eventually in society. And so again, came up the need for more real-world deployments, because of course we want to make sure that what we propose works in the real world before it's adopted. And then also it was pointed out that what the CPS program has been doing in collaborating with different agencies such as NIFA, DOE, et cetera, is actually a great stimulus in order to foster this type of interdisciplinary collaborations that can bring some advancement that can actually have more impact in the industry and society. So again, as I just said, so support interdisciplinary teams and interdisciplinary projects. Also, for some systems, when they are tested and designed, we should really understand what are the assumptions that we are considering, because when we implement this system in practical systems that deal with probably with operating systems which are not ideal, with different devices that deal with different operating systems. So some of the assumptions, like for example, the type of communications of bandwidth or delay, et cetera, that we can achieve may be actually different than what it is just because of the software that is running on these devices. And finally, there was agreement among all our speakers that we need to work also on the acceptance of technologies in order to ensure that we collaborate, for example, with social scientists, and we make sure that our technologies address real problems and they can actually be accepted by the final stakeholders. So they're not just nice and elegant scientific solution, but it's something which is developed in accordance and together with the communities in order to at least improve the chance that these technologies are going to be adopted. And this concludes my presentation. Thank you. Thank you, and this also concludes the session. I think after this we're going to have the posters. There are going to be some over here and some over there. Please enjoy, and thank you.